A continued growth of the world population is expected, where it is estimated that in 2050, there will be more than 10 billion inhabitants in our planet, and approximately 70% of the population will live in cities. This represents a challenge to supply food to the population concentrated in urban areas in a sustainable way. Humanity is also facing a climate emergency that causes an increase in desertification, which threatens the availability of water as a fundamental resource in food production, where only 1% of the planet's water is fresh. Therefore, considering the limitation of natural resources accentuated by climate change, we must implement solutions to ensure food supply security, to meet the demand of the current and future population. Smart Biosystem proposes the decentralization of food production through fully autonomous vertical farming modules. With this strategy, we minimize the carbon footprint by reducing the transport of food production to consumers. Each module can function autonomously in terms of both energy and the crop growing process. The module's energy source is solar-based, utilizing photovoltaic panels to harness energy from the sun. Additionally, an energy storage system is integrated to provide power during nighttime hours. The module is designed with an enclosed system to establish a controlled interior mesocosm. This approach facilitates the regulation of environmental factors such as temperature and humidity within the module. As a result, the growth process within the module remains unaffected by the extremity of external environmental conditions. An internal air cooling system is incorporated to regulate temperature, accompanied by a humidity control device to manage this parameter as well. Let's take a closer look at our solution approach. The sun emits significantly more energy than any other artificial light source. It also emits all the energy required for the photosynthesis process within the red and blue regions of the light spectrum. In simpler terms, plant growth is enhanced in the presence of sunlight, due to the inability of artificial lighting to precisely replicate the specific wavelengths that are most favorable for plants. Therefore, in geographical areas where sunlight is abundant, we consider this to be the most favorable approach. The module is outfitted with sensors to automate the preparation of nutrient solutions, and precisely water the plants within a closed-loop high-pressure aeroponics configuration. This dynamic process adapts the nutrient composition according to the plant's growth stage. Concurrently, plant monitoring is achieved through cameras situated both within the module and on external drones. This entire process is seamlessly managed through the implementation of machine learning and AI, guaranteeing that the plants thrive under the best possible internal conditions and receive appropriate nutrient concentrations based on their developmental stage. In addition to the fully autonomous off-grid operation of the device, the module will incorporate IoT communication protocols. These protocols will enable remote control and monitoring of the system's proper functionality. Moreover, in case of any failure, we can promptly detect the issue and attempt to resolve it remotely. To enable large-scale vegetable production, we are departing from the conventional tray-based approach, commonly employed in modern indoor vertical farming. Instead, we suggest employing high-volume growing chambers to optimize root growth potential. These growing chambers will incorporate specialized nozzles, enabling the application of high-pressure aeroponics, a technique that involves spraying the roots with the nutritive solution through these nozzles. The vertical farming module will integrate multiple collectors housing several growing chambers. To accommodate the growth of various plants with unique nutritional requirements, the module is structured with an architecture of independent collectors. Each collector is controlled by its own electrovalve, enabling the application of a customized nutrient solution composition for each individual collector. This method supports the cultivation of a diverse range of plants within the module, which contributes to increasing plant biodiversity. Where and how can these modules be utilized and placed? The module has been designed with scalability in mind, making it adaptable to various scenarios. On a smaller domestic scale, For instance, we can install one or multiple vertical farming modules within our homes to provide fresh vegetables for a family's consumption. The concept behind this idea is to offer a plug-and-play device, eliminating the need for any agricultural expertise in order to grow vegetables. This approach enables the system to operate completely autonomously. On a larger scale, in order to provide vegetables to a community residing in apartment complexes, a larger number of modules can be deployed. Considering the impact of climate change and the scarcity of water as a precious natural resource, we can efficiently achieve fully autonomous and decentralized food production through the utilization of solar energy, regardless of the extreme weather conditions.